We are still in chapter 4, Industrial Robotics. Let's continue with part 2 of chapter 4. Okay, now let's move to the next topics, which is robot anatomy. What is robot anatomy? Have you ever heard about robot anatomy? Um, Merriam-Webster Dictionary define anatomy as a branch of biology concerned with the study of the structure of organisms and their parts. Therefore, robot anatomy deals with the study of different joints and links and other aspects of the manipulator's physical constructions. The right figure shows the anatomy of Robocop. Okay, so mechanically, a robot manipulator is composed of two sections. Okay, so as you can see, the left side is the first section of a robot manipulator called as body and arm assembly. Why this part is called as body and arm assembly? Because this section consists of body and arm parts only. As you can see in the slide, body and arm assembly only covers from this part, we call it as waist, up to this part only, which is before the wrist part. Meanwhile, the right side is the second section of a robot manipulator called as wrist assembly. So there are two sections. The first section is called as body and arm assembly, and the second section is wrist assembly. Why this part is called as wrist assembly? Okay, because this section consists of wrist part only, and as you can see, wrist only cover from this part up to this part. Okay, so this part is called as wrist assembly, and the first part is called as body and arm assembly. So same goes to the second picture. From waist to wrist, this is the first section, and from wrist to tool is the second section. Okay, so as mentioned earlier, um, our main focus for this chapter is industrial robots. Robot arm, or we call as a manipulator, is one of the most important components in industrial robots. So robot manipulator is one of the most important components in industrial robots. So industrial robot manipulator consists of joint and link. So what is joint and what is link? As you can see from both figures, the dotted red are the joint of human arm and a robot arm. Meanwhile, the blue line here are the links for human arm and robot arm. Okay, figure in the slide shows some of an important elements for a robot manipulator. So base, as you can see here, base is the first end of the manipulator, and it is face. Base is face, and it is used to support the robot. And the second part is joint. So joint in manipulator provide relative motions, which means that robot are the movable parts in manipulator. Okay, so these are the joint 1 and joint 2, and The other elements is links. So what is link? Link is placed between joints. So link is placed between joint. For this case, so we have link 0 and link 2 for joint 1, and we have link 1 and link 2 for joint 2. So link is placed between joints, and link is rigid compared to joint which is movable. And the last part is we call as an effector. So an effector is used to manipulate objects or perform assembly tasks. So this is the an effector, or we call as an of arm. Okay, so let's move to the first element, which is a robot joint. So what is a robot joint? Robot joint is also called as axis, and it is actually similar to joint in a human body. So these are the joints, okay, for human arm. Robot joint can move. Okay, so as mentioned just now, robot joints are the movable components, and a robot joint can make relative motions between adjacent link. So these are the joints for robot arm. Okay, so robot joints, robot arms are described by a DOF, or degree of freedoms. So for each DOF, a joint is required. A higher number of DOF indicates an increased flexibility in positioning tool, meaning that the higher the number of degree of freedom, the more flexible the robot positioning tool. So I repeat, the number of degree of freedom indicates an increased flexibility in the positioning tool of a robot. Okay, so figure in the right illustrate the 6 DOF robot arm. Why 6 DOF? Because as you can see, there are 6 joints for this picture. So there are joint 1, joint 2, joint 3, joint 4, joint 5, and joint 6. So this robot arm has 6 DOF. Also reported that most industrial robots possess 5 or 6 degree of freedom. Okay, so left figure shows robot with a 3 DOF, while the right figure shows a robot with 6 DOF. From both figures, we can see that the higher the number of DOF, the more flexible the robot is. So the higher the number of DOF, the more flexible the robot is. This figure shows a 5 DOF robot arm. Okay, um, and this figure also the robot arm with a 5 degree of freedom. As you can see, there are 5 joints and 5 independent movement the robot has. So this is the first joint, second, third, fourth, and fifth. So this robot is a 5 degree of freedom robot arm, and the first movement is to rotate the robot waist. The second movement is to rotate the shoulder. The third movement is to rotate the elbow. The fourth joint is used to rotate the wrist, and the last joint is used to rotate the gripper. This slide illustrates the DOF for human arm and DOF for a robot arm. Okay, so what causes the robot joint to move? What causes the robot joint to move? Okay, so each of the robot's joint is driven either a DC motor, AC motor, stepper motor, hydraulic piston or pneumatic piston. So left figure shows a robot driven by a DC motor. So these are the DC motor which drive the robot. Okay, and the right figure here shows a robot driven by pneumatic piston. So these are the pneumatic piston used to drive the robot arm. Okay, so this slide shows five DOF robot arm. Why five? Because we have five joint. So joint one, joint two, joint three, joint four, and joint five. So this is five DOF robot arm, and um, the right side here shows its control system. As you can see, there are five motors used to drive the joints. So this is motor 1, motor 2, motor 3, motor 4 and motor 5. Motor 5 is used to drive joint 1, motor 2 is used to drive joint 2 and so on. Okay, basically, robot types can be categorized into two, which are translational and rotary. So type L and type O are translational joint. Meanwhile, type R, type T, and type V are rotary joint. Okay, so linear joint is always called as type L joint. For this type, the movement between input link and output link is linear. Uh, for this picture, the moving part for type L joint is this one. So this is the moving part, the blue one. Okay, so in order to view the video, I suggest you to scan this QR code. Next, we have orthogonal joint or type O joint. The movement between input and output is also linear, but the input and output links are perpendicular to each other. So in this case, this is the input link and this is the output link. So for this case, the moving part for type O joint is the yellow one. So this is the moving part. So for illustration, please scan the QR code. Okay, now is rotational joint or type R joint. Okay, type R joint. So type R joint provide rotational relative motions of the joints with axis of rotation perpendicular to the axis of the input and output links. When you scan this QR code, you can see that um, the moving part in this joint is uh, this one. So this is the moving part for rotational joint or type R joint. Okay. So the rotational joint or type R joint is a rotary type joint. Remember, we have two types of joint, linear and rotary. So this is for the second type, which is rotary type. Okay, and then we have a twisting joint, also the rotary joint. So twisting joint, or sometimes we call as type T joint, uh, make twisting motion among the input and output. So when you scan this QR code, you can see that this part will twisting. And lastly, we have revolving joint or type V for rotary types joint. So in this joint, the output link axis is perpendicular to the rotational axis. So the output link is perpendicular to the rotational axis. Okay, so for illustrations, please scan this QR code. Okay, so we have learned about robot joints. Now let's move to robot links. So what is robot link? Robot link is a rigid components that form a chain connected together by joints. So as mentioned just now, the blue line here are the robot links. So a robot link is a rigid, okay, compared to a robot joint. Robot link cannot move. Okay, so each joint has two links. Each joint has two links. What does it mean? If each joint has two links. Okay, so most robots are mounted on a stationary base. Okay, so we call as a base, robot base. Okay, so the first link connected to the first joint is link 0. So the first link which is connected to the robot base is called as link 0. And then the output link, okay, the output link is uh, link 1. So the output link is also connected to the first join. So first join has input link and output link. So same goes to the subsequent join, which is join 2. So join 2 also has two links. So this is the input link, which is link 1, and this is the output link, which is link 2 for join 2. Figure in the slide shows the similarities of human body parts, okay, and robot parts. The first part of the body is known as the base. So this part, okay, this part, the fixed one is the robot base. The second part is the shoulder, okay, shoulder, elbow, wrist, and the last one is an effector. Okay, in learning robot, you must remember all these parts. So you must remember all these parts from base to an effector. Okay, now let's move to robot joint notation scheme. So what is joint notation scheme? Have you ever heard about joint notation scheme? Robot joint notation scheme use joint symbol type L, type O, type R, type T, type V. To design it, joint types used to construct robot manipulator. And for example, the manipulator has notation scheme of R, R, semicolon, T. So this manipulator has a notation scheme of R, R, semicolon, T. Why? Because the first section, okay, remember this is the first section, body and arm assembly. So the first section involved with type R and type R joint, type R and type R joint. Meanwhile, the second section involved with type T joint. So the joint notation must be read from base or body arm section to wrist section. So must start from base to wrist section. Okay, try to do exercise, this exercise by your own. Try to do this by your own. Okay, so body and arm, wrist, and effector parts are important parts for robot arm or robot manipulator. So these are the body and arm, okay, and this is the wrist, and this is the end effector. So all these three are the most important parts for robot arm or robot manipulator. Okay, let's take a look on the first part, which is body and arm. Okay, so body and arm. The main function of body and arm is to position an effector, such as clipper or tool, in space. So the main function of body and arm is, as mentioned just now, is to position an effector in space. Essentially, industrial robot manipulator has five configurations, which are polar coordinate body and arm assembly, cylindrical body and arm assembly, Cartesian, jointed arm, and SCARA, or selective compliance assembly robot arm. Okay, polar coordinate or spherical robot consists of a sliding arm or L joint, um, type T, okay, T joint, and type R joint. I hope that you still remember what is type T, type R, and type L is. Okay, type T is a twisting type joint. This type of joint make twisting motion among the output and input. So this joint type T make twisting motion among the output and input. So type R is a rotational type joint, and type L is linear type joint. So polar coordinate or spherical robot consists of R, T, and L joint. All this arrow, okay, as you can see, so all this arrow shows the motion of the joint. So this is the motion for R, for T, and for L. Now, can you guess what shape of envelope will be produced by polar robot? So this is the polar robot, right? So this is the polar robot, this is the polar robot. So can you guess shape, what shape of envelope will be produced by a polar robot? Okay, so polar coordinate robot, okay, produce this shape. So what is this shape? So this is a spherical work envelope. So this is an example of a spherical work envelope produced by polar or spherical robot. Okay, the next robot arm or manipulator often found in industry is a cylindrical robot. So cylindrical robot consists of type T, type L, and type O joint. So type T, type L, and type O joint. So normally we read from base to an effector. So the joint notation is always read from base to an effector. Okay, so this is cylindrical robot, consists of three joint T, L, and O. Okay, now can you guess what shape of envelope that will be produced by this robot? Okay, so this is the answer for the question. So the cylindrical robot produce cylindrical envelope. Okay, so this is the cylindrical shape. Okay, so this is a Cartesian robot. Certain industries call this robot as XYZ robot. So Cartesian robot doesn't involve with any rotary motion. Okay. As you can see, this type of robot only consists of linear motion, which is type L and type O joint. So this robot consists of type L, type O, and type O joint. Atlas 2500 series by Alpha Robot, which is used for pick and place operation, is one of the Cartesian robot often found in industry. Okay, so Cartesian robot produce rectangular work envelope, as you can see. So this is the rectangular shape produced by Cartesian robot. Okay, so next is a jointed arm or articulated robot. So this type of robot configuration is said similar to human arm. Okay, so as you can see, this robot, yeah, it seems similar to human arm, and this jointed arm robot consists of type T, type R, and type R joint. So T, R, and R joint. Okay, so like a polar robot, jointed arm robot produce spherical work envelope. And lastly, we have SCARA, or selective compliant assembly robot arm. Okay, so SCARA robot is said similar to jointed arm, except that vertical axes are used for shoulder and elbow joints to be compliant in horizontal direction for vertical insertion tasks. SCARA involved with type V, type R, and type O joint. So V, okay, starting from base, V, R, and O joint. Okay, now what shape of envelope that will produced by SCARA robot? Okay, so SCARA robot produce irregular work envelope. So this is the shape, example of shape produced by SCARA robot. Irregular shape. Okay, and this table summarize the type of robot arm. Okay, the type of robot arm such as Cartesian, cylindrical, spherical, scara, and articulated, with the shape of envelope produced by this robot. For example, Cartesian robot produce rectangular work envelope, cylindrical robot produce cylinder work envelope, and so on. Okay, try to match the manipulator with the shape of envelope that will be produced. Scan this QR code to get more information regarding body and arm configurations. Okay, so end for part 2 of chapter 4. Thank you for watching. See you in the next lecture.